Let me switch gear, and now I'm going to tell you about more discrete kind of rearrangement, and I want to start with plasticity. In fact, most of the time I will be discussing about plasticity of a soft system. So again, think about your packing of particles, but compressed, or mayonnaise, or something like this. And in the last decade, plasticity of such disordered solid has actually been studied a lot. So what you can do is put your mayonnaise, if you want, in the rheometer, and then you're going to impose a strain, a change of the aspect of your system, shear gamma. So you can do this as an experiment. You put your system, you impose a strain, let's say very slowly, and then you can measure the stress, the restoring force in your rheometer. And after some transient, that depend on how you prepare your system, actually, you will reach a plateau. That's if you do it quasi-statically. If you are doing it at a larger strain rate, this plateau value would increase, and it's just a singular flow curve I told you about before, but here let's just think about this very slow drive of the system. So this plateau defines this yield stress. It's a plateau, but for example, if you look at it numerically, in a finite size system, and you zoom in and you really look at the stress, what you find is that this stress, or this is the stress here, actually has a sort of ratchet behavior. So you have regions where you can actually load elastic energy smoothly, right? So that's different from a granular material where particles are hard. Here you can actually load elastic energy. So you have those ramps that go up. But then you have discrete time point where, boom, you have plasticity and you release this energy. And you have drops in the stress. So you have some kind of intermittent dynamics. And those drops can be small or they can be very large. Actually, they are power law distributed. And then you can look in real space in those numerics, but actually not only numerics, that's what's also nice about it. But if you look in numerics and you look at actually how the particles have moved between those 2 points, so that's a displacement field. Here it's a projection of the displacement field in one direction. What you find is that those plastic rearrangements are fractal objects. So I don't know if you can see from here, but you have some kind of elongated, very anisotropic microfracture in the system, like this, but then you also have crosses here where you have it's smaller and also on this side. And so if you look at them, you can identify power laws that describe their geometry. Actually, it's nice that it's also seen in experiment. So this is using a technique called DWS, where okay, I'm not going to enter in the detail. It's an analysis of the speckle, but you can detect plastic strains that are extremely small, like 10⁻⁶, so very tiny displacement of the particles. So you increase the stress, and then you have plasticity appears in red here, and where it's not plastic, it's in yellow. And you have the sort of structures that you can visualize, and you see that they form elongated bands like that. At this point, when you're here, you have, in this setup, in this geometry, you have shear bands, macroscopic breaking of the system. But you have this kind of avalanche-like property that you can actually visualize in experiment. One result I want to discuss that we can get from what I will tell you concerns the following question. When do you have this kind of avalanche-type response? And when is it that those avalanches are... Here, if you look here, for example, you see that the big avalanches completely span your system. They are system spanning. And the question is, but that's very special. You are at a critical point. You're right at sigma c, the sort of stress that's the yield stress. What if you're below the yield stress? So I will argue that even if you're below the yield stress, the entire solid phase, as long as you have plasticity, I will argue is critical, that those objects have correlation lengths that span the system. Okay, so the nature of the excitation, the elementary rearrangement in this system is well known for decades, and they are called shear transformations. So again, think about this system where you have your particles and you impose a strain on it. You have an elastic energy, so it was E before, it's U here. And you can ask, what happens? You load elastic energy. What happens when suddenly you have a plastic event? What it means is that you had a saddle node instability in the system. So one direction became unstable. Okay. Now, with the computer, you can look in real space what really initiates this plasticity, and it looks like that. So what you find is that it's mostly localized. So, for example, if you were shearing like this, you could have particles that were initially like that. Locally, they change contact, for example, something like this. Right, so those guys have moved, and those guys were pulled in that direction. So you have a local rearrangement, but this local rearrangement, you're in an elastic medium, it's going to correspond to a local strain. So it's going to change the stress elsewhere in the system.
So this is before the...
So this is, if you want, this is the mode. For example, what people do in computers is they analyze these modes that become flat. So that would look like this. So it's really the mode that became unstable. But then, once you go along it, much more can happen, right? Because this guy is going to relax by a finite amount, right? So even if it was the only thing that would happen in the system, it would rearrange by a finite amount. That's why I would call this excitation discrete. It's not like in the soft elastic mode where you can move continuously here. If it decides to relax, it relaxes by a finite amount. But once you relax, then you change the stress everywhere in the system, and so you can trigger something elsewhere. So a shear transformation here can trigger another shear transformation there, and so on. And those big avalanches are presumably thousands of objects like that organized in some specific way. What should I say about it? So I should tell you that because it's local, the drop of stress induced just by one guy should go like 1 over the system size. That's something I will use. Right. And so the question I want to discuss is, how many objects like that do you have in a mayonnaise or in a packing of particles? How many of those shear transformations are about to collapse? Right? That's clearly very important if you want to think about those avalanches, because it will characterize the probabilities that one guy trigger other guys. So how do you even start thinking about this density? And here is an interesting quantity. So let's think about it that way. So let's cut our system into blocks. And those blocks have to be of size larger than 1, much larger than those shear transformation, okay? In each block, I can introduce a variable xi, which is how much shear stress can I put on this block I to have a plastic event in it, okay? So it's a sort of local distance to yield stress. So it's related to, if you were looking at this block, what is the slope of the most dangerous, most likely to collapse mode? All right, so in each block you have this xi, a sort of distance to the local yield stress. One quantity that's very important is a distribution, P of x, of those xi. Okay, it turned out that P of x itself, well, you could try to measure it like that by decomposing the system in blocks and trying to get xi. And actually, there are recent papers on that claim that they can do it like this. what's problematic when you do that is that typically people pin the boundaries of those blocks, and if you pin the boundaries of the blocks, you actually stabilize it. So then I think you should have a systematic bias that increases those xi, but some people claim that they can do it. I think there is an elegant way to do it that was previously done. And that was a statement, oh, maybe having the full distribution P of x is very hard. But one thing that you can extract is a minimal value, x mean. Why can you extract x mean? So if you look at all those blocks, you can look at the most dangerous one. Well, you can extract x mean because it's just the stress you have to add on the system before any event takes place. Right? Because the guy that is going to be triggered is actually x mean. So for example, imagine you're here. X mean would just correspond to how much additional stress I can put before I have one single event. Is it clear? Yes? All right. So in this kind of procedure, when you have a finite size system and you have this crackling, you can get X mean just by looking at the size of those ramps. And then you can use extreme value statistics, right? If you know a distribution P of x and you have n variables and you assume they are independent, then you can relate x mean to P of x. All right, so what was this thing? Okay, and the observation, okay, so the observation that was made, Lemaitre, Caroli, but there is also Procaccia and others, and Lerner. So they made the following, I can phrase it like that. So they measure this quantity, and naively, what would you think it should behave like? Naively, you would think that this quantity should go like 1 over n. This is the rate at which you trigger plastic event. So, right, so if you have a block of mayonnaise, you have a given rate. If you have a block that's twice bigger, you would think that this rate at which you have plastic event is twice larger. And they found out that it's not. They found out that it's surprising that if you take the system which is made of 2 blocks of mayonnaise, it's actually more stable than what you would think. So what it means is that how this scale with system size does not go like 1 over n, it goes like 1 over n to the beta, where beta is actually smaller than 1. So very large systems are actually more stable than what you would think. Now, I'm not going to derive it, but it's just extreme value statistic. One interpretation, the explanation, if you want, of this exponent beta, is just that P of x, okay, you would get actually 1 over n if the distribution P of x would not vanish in 0. But you would get a non-trivial exponent beta if x has what's called a pseudo gap. It means that the density of excitation goes like x to an exponent theta, which is positive. If you have that, you can work it out, and you find the relationship between beta and theta, and beta is just 1 over 1 plus theta. So from those kind of just those finite size measurement and this extreme value statistics argument, they can get values of theta in 2 dimensions and 3 dimensions. Okay. All right. So what I want to those exponents we have argued are important if you want to think about the liquid phase, and that's in this paper, but I'm not going to review it. So what I would like to, the only thing I would like to show instead is why you have a pseudo gap, why theta must be larger than 0. And already when you know that, you can draw consequences from this that are interesting. So that's, I would just like to stick to that. And that's where you have an argument of stability. The fact that the system does not live close to a giant cliff in a landscape picture, here will mean the following. Imagine that I trigger a shear transformation at the origin of the material. it's going to change the stress elsewhere in the system. Okay, I can tell you now, how is it going to change the stress? Well, a shear transformation like that is not a monopole of force, it's a strain, so it has to be dipolar. So it would just decrease in amplitude, in stress, like a dipole, which goes like 1 over r to the d. Then, in average, it also has some spatial structure, and the details, I'm not even going to tell you what is phi. The only thing I will tell you is that when you have a shear transformation that relaxes, it destabilizes some region, but it does stabilize other region, in average. Okay, I'm just going to take this for granted. So it gives a kick to the system in stress. This kick can in turn trigger a new shear transformation. Okay, now I want to prove that P of x has a pseudo gap. And the way I'm going to prove it, the argument is as follows. I will argue that if it didn't have a pseudo gap, then when you trigger one shear transformation, as soon as you trigger one, you would trigger many others. Each of those many others would itself trigger many others, and you would have a catastrophe, and your mayonnaise would suddenly be completely liquid. You would have extensive rearrangement in the system. So to avoid this extensive rearrangement, you must have a pseudo gap. So let me compute this mean, assume that there is no pseudo gap, and let's compute this mean number of event m that would be triggered by one shear transformation. Okay, so what is m? It's going to be an integral on space, because I can trigger things everywhere. The probability to trigger something over there will be proportional to the amplitude of the kick there. I told you it goes like 1 over r to the d. And to the distribution of shear transformations that are about to collapse close to 0, p naught. This is, I'm assuming that there is no pseudo gap. I'm assuming that this quantity is not vanishing. And it's an integral on space. And then you just look at it and you see that it goes like the log of the system size. So if there was no pseudo gap, as soon as you trigger one guy, you would at least trigger log L new shear transformation, and then you would start to have many activity in your system. You would have an explosion, so it cannot be the case. So that proves that you must have a pseudo gap and that theta must be larger than 0. Note that this argument is true for the entire solid phase, right? Not just at sigma c, it's true all the time. You must be stable. It cannot be that in the solid phase, as soon as I touch it a little bit, boom, I'm completely rearranging. Okay, now one point. So here we get, and that's typical when we have those discrete excitation, the sort of stability argument lead to a bound on exponents. When this bound is saturated, we'll refer to marginal stability. Here in this case, actually, the bound is not saturated. I told you those exponent theta are actually strictly larger than 0. And so stability alone is not enough to fight this sort of sampling problem I told you about. It does not tell you where you live in which configuration are visited. And in fact, in this case, to build a theory of theta, we needed to really build a description of the dynamics. And we could do it in a mean field setting that seems to work well in 4 dimensions, maybe exactly, and in 3D it's pretty good. But I don't have time to talk about it, so I can take question about that. But really, you have to do dynamics. Then we find that this exponent theta can even depend on system preparation, but in a way that we can predict at least some aspect of it. Okay, so here I just want to say that. Oh yes, I want to say that, and it's a general argument about glassy systems that have a pseudo gap. That as soon as you have a pseudo gap, it means that the entire solid phase crackles. So for those that are used to this crackling idea, it's very well known, for example, for the depinning problem of an elastic manifold in a disordered environment. The example, if you have a drop of water on your windshield, if the drop is too small, it gets stuck there because the disorder on the glass is strong enough to pin the contact line. If the drop is big enough, boom, it falls. It's well known that when you're close to this critical force where it can move, that you have very intermittent avalanche type response. But if you're below this critical force, you don't have that at all. Okay? Here I'm saying that it's very different from depinning, that actually in those glassy systems, as long as you have a pseudo gap, and you must have it if you have long range interaction, in fact, that the entire solid phase must crackle. So the experiments that were showing this sort of plastic rearrangement, I'm claiming that as soon as you have intensive plasticity in the system, that this avalanche must be system spanning. Okay, so that's the argument. So before I extend it to the solid phase, let's look at this at this sigma c. So you shear the system, and you reach a plateau for the stress-strain relation. And I told you this plateau, you go up and down. Essentially, the idea of the argument is that when you have a pseudo gap, I told you that how much you can go up is much larger than 1 over n. It's unusually large. Which means, and in average, how much you go up and how much you go down have to be equal. So it means that you have to go down by big jumps in average. It's as simple as that, the argument at the end. Right, so I told you that how much you go up, this x mean, it's much larger than 1 over n. How much you go down? So those are the avalanches of many shear transformations. S is the number of discrete events in an avalanche. Each of those discrete events reduces the stress by 1 over n. So this is the number of events in an avalanche divided by n, this drop here. But because how much you drop must be how much you go up in average, and how much you go up is much larger than 1 over n, then it means that S is much larger than 1. In fact, if you work it out, it has to be n to this power of theta. Yes?
These averages are time averages, or are they average over events?
Well, it's just average. It's just, here I'm just using the fact that you reach a stationary state for the stress. So it's average. Imagine that you strain it for a very long time.
Yeah.
And then you average on this very long...
Because in principle, you could go up in one step and then do many little steps down and then go up in one step, right?
You could go up in one step and do many... Yes, but for the average, that would still be true, what I'm saying. If you go, I mean, if you go up, yeah. Every step is... when you go, I mean, you have to... when you go down, you have to go up before.
Okay.
Right. All right. So in some sense, systems that have a pseudo gap are unusually stable. That they trigger, you trigger plasticity very rarely. So when you trigger it, it has to be large. So that does not surprise anyone who has thought about depinning or things like that, because that was at the critical stress. But it turned out that this argument must also be true in the solid phase, as long as you have some finite amount of plasticity. So what I mean by finite amount of plasticity is that, for example, if you look at, sorry, all my slides are cut, but if you're looking at the stress versus the strain, if you go up and down, I mean that in the thermodynamic limit, you still have a finite drop of stress. Right? And so in this region, you had a finite amount of plasticity. If you have a finite amount of plasticity, well, this argument goes through, because you don't need that how much you go up and how much you go down are exactly the same. You just need that they are of the same order as n varies. And so it's also going to be true here. The amount of plasticity and the amount of elastic loading are comparable if you have an intensive plasticity. So this argument, again, tells you that in the entire solid phase, if you do have plasticity, those avalanches their mean must grow as a power of n. The only way you can do that is if their length scale has a cutoff, which is the system size. So this states that in those systems, when you have avalanche response, when you have plasticity, then it must be system spanning. And this is this simple argument is actually valid for any glassy system which have which have a pseudo gap. So you can think about spin glasses with sufficiently long range interaction, electron glasses, hard spheres, I'm going to tell you now, and so on. Any questions? I have one here.
What is actually gap? What is the gap?
Why do I call it pseudo gap?
Yeah, but what quantity shows this exhibits a pseudo gap?
So it's this. So the quantity that exhibits the pseudo gap is this P of x. So that's the density of shear transformations that are at the distance x in stress to collapse.
So it doesn't go linear into zero, it doesn't go close to zero.
So one case that could have, that you cannot exclude with this argument, is that you would have a hard gap. And then the system would show no plasticity at all. And that would be fine with this argument. It would just say there is nothing. But if there is intensive plasticity going on, then this argument shows that it must be by system spanning events.
With the combination of plasticity and long range.
Yes, so it's very important. So in all those systems, it's a long-range interaction that leads to the pseudo-gap behavior.
And is there dissipation in the kernel, like the Shelby or the other one? Like the stress is conserved?
Ah.
Because you have a scalar stress, no?
Okay. So there are many questions in one. We'll choose your question. No. I mean. Okay, so there are several. I mean, one aspect is that it's true that G should be a tensor quantity, all right? But in this argument, it was just scaling, it would not matter. Now, I don't think it's your question, but maybe it's interesting that some people who model the yielding transition with simple automaton dynamical model like those, if they put scalar propagator or a tensorial one, they seem to find the same scaling behavior. But for this argument, it's clear that it doesn't matter. It's just, I mean, that the tensorial nature is not going to change anything. It's just the scale at which you can trigger something. But that was just one part. You had another.
Yeah, my question was more or less like what you call plasticity is all the rearrangements that you're talking about here are like plasticity.
Yeah. Yeah, I mean, I would call it plasticity, and then this is some elastic branch where you have no plasticity, and then you have this plastic event, right, where you drop. In this numerics, it's done at fixed strain. So the stress is dropping. You can also do those numerics at fixed stress, at increasing stress, and then you. But at some point, boom, you have avalanches that never stops. But you can do both in the solid. Yes.
And the finite system would have a little gap.
Oh yeah. Well, yeah, exactly. So the little gap it has is this typical value.
So when
This is.
when people I don't know, put carbon into iron or something, is it like making it finite and creating a gap or something like that? I am
Okay, so are you bringing me to crystals? Because I could. I mean, but I think it should hold there too. Because what happens in crystals is that you have dislocations, but they are entangled. Actually, what would play the role of X, I mean, if you shear a system like that, it's seen that you have avalanche-type response in systems of dislocation. And you can think about a dislocation that will have a weak region that would, you can also define this X. That corresponds to motion of dislocations that were entangled, but if the stress becomes larger than some threshold, one can start to move. And the kernel is just the same. The motion of a dislocation is the same kernel that I discussed. So then I think all these same arguments should go through.
And when they put things that will really stop these dislocations, I don't know when they put.
Well, dislocation system is indeed more complicated because you have stress hardening and the density of dislocation can change in time, so it's hard to reach a stationary state and so on. But as far as discussing the fact that the solid phase should have a system spanning event. I think it should be true. I mean, you can imagine more complicated. Those dislocations could assemble into grain boundaries, and you could have also very different physics. But just this one aspect I'm mentioning, I think it should be true. But okay, but I didn't answer the question. No, behind you. Okay. All right. Okay, so it's, and then for completeness, I wanted to, yeah, because right. I wanted to talk about the third kind of excitation, and now I'm changing system again. I'm going more towards the granular systems, a simplified version where you don't have friction. We're trying to work it out when you have friction, but so let's think about plasticity in a system where particles are completely hard. Hard frictionless particles. So, for example, think about this system: hard frictional disks pushed against each other. And now you have to ask, what are the excitation there? And so the one way to think about it is think about the system confined at some pressure, and then again you put a shear stress on it. So for example, the force along here was initially equal to the force along here, but now you're going to add this mu and grow it from 0. So you had a packing of infinitely hard particles, and now you start changing the forces adiabatically. Initially, the system is not going to move strictly because particles are infinitely hard. Unlike in the soft system where you had elastic branches, now nothing can happen in terms of displacement of the particles. The stress can change inside, but the particles stay at the same location. That's going to hold until one force goes to 0. So then you have all the forces between particles have to be repulsive. At some point when you change the stress, one forces go to 0. When this goes to 0, you break a contact. Okay, something else I hope Andrea told you is that those systems are, for frictionless, infinitely hard particles, are isostatics. Well, we discussed it a bit already. They are right at the Maxwell threshold. They just have enough constraint to be mechanically stable. So in this geometry, if one contact force goes negative, goes to 0, and one contact open, suddenly you have 1 degree of freedom in the system. But this 1 degree of freedom is very different from a shear transformation, at least when you have frictionless particles. And that's because elasticity at this Maxwell threshold is critical, as we discussed. So this one contact open, you have one mode that goes to 0. You have one constraint that's removed. It means that you have one floppy mode in the system. This one floppy mode is completely extended in the system. So that's very different, again, from a shear transformation that would be polar law decaying. And that comes from the fact that the system is critical as far as its elasticity is concerned. You can actually give argument as to why it has to be extended, but let's assume it now. So you push this contact, you stress the system, one force went to 0, suddenly this contact wants to open, it's moving all the particles around. And that's this blue displacement field that you see here. Okay? So actually, those are the excitation I'm talking about. It's rupturing one contact, and actually, you're going to move until you create a new contact elsewhere. So this excitation is really a sort of change, removing one contact somewhere and adding it elsewhere. So it's, again, a discrete excitation because it's a finite, well-defined amount of displacement you have to do that. Okay, again, you can think about the stability of an excitation like that. And here, I'm not going to derive it. It's done there. But I just want to give you the intuition. So one way to phrase the problem is to think about, imagine I change the stress on the box. I have one contact that open, and then I have this collective rearrangement in the entire system. and these contacts that open, things move, and maybe it's going to close a new contact there. When this new contact closes, the system can be stable, or in this new configuration, there can still be negative forces, and then you would again trigger some kind of more and more rearrangement, and you can have avalanche type response. So again, you can do an argument and ask, under which condition will it not explode? One contact opening and closing will not trigger, an immense number of new contacts opening and closing. So the two things that are important ends up being the distribution of forces and the distribution of gaps between particles. So I think I'm not going to derive, but I'm going to tell you intuitively why it's like that. If you have many weak forces in your system, it's clear that it's going to be more fragile. Because when you have an excitation like that, you shift things around. If you had many contacts that were at very small forces, it's likely that they will open in turn. So again, to be stable, you would like to have a pseudo gap in the distribution of forces. You don't want to have that many forces that are about to yield. And the other aspect that plays a role is the distribution of gaps. And here, again, if the gaps are all too big, it means that when one contact opens, it's going to be hard to make a new contact, so you will move everything a lot. If you move everything a lot, it's more likely that it would lead to instabilities later on. Okay, you can work it out quantitatively, but that's... so at the end, what you get is... Let's assume that the distribution function of those gaps has a power law behavior, and the distribution of forces has also a power law behavior. I introduce an exponent theta e here, which disappeared. What you get, with respect qualitatively what I told you, is a relationship between those two exponents. Okay? So it's very similar to the shear transformation discussion. You think about stability of discrete excitation, and you get a relationship between exponents. Before we had just one exponent, now we have two. Now you can check numerically, and that's what Edan Lerner did. You can check what is the value of gamma and what is the value of theta e. And what you find is that this inequality in packings appears to be saturated. So once again, there is a pseudo gap in the force distribution. You don't have that many forces that are weak, and you do it in such a way that the system is stable, but barely so. All right, so that's an observation. Actually, in this case, you can prove that this inequality, even in finite dimension, you can prove that this inequality must be saturated. So you can prove this marginality. And in fact, this proof is really due to the fact that even in finite dimension, I have effectively what is an infinite range interaction. And that comes from the fact that those excitations, if I open a contact and close one, are completely extended in the entire system. In fact, the argument we give to prove that this inequality is saturated also holds for mean field spin glasses, for example, at 0 temperature. I can answer a question on it, but I was not planning to. What happened later is an exact calculation in infinite dimension where theta e could be computed and also this gamma, and that was actually confirming this marginal stability, but also giving this value of theta e that was not constrained by this marginal stability argument, was giving it in infinite dimension, and it seems to be also good in finite dimension, this exponent. And the last thing to say about that is that we think that an entire theory, quantitative theory of inertial flows and suspension flows can be written in terms of this theta e, and it's completely, it predicts, all the exponents of the problem, and it seems to work very well. But I will not talk about it because I think Eric at the last meeting spent 30 minutes talking precisely about that. Okay, so that was in some sense where I wanted to conclude. It's a summary of what we discussed. And it's sort of classification of of those excitations that are important for plasticity or linear response in those systems. And we talked about 3 of them, those soft elastic modes, which we call anomalous modes, those shear transformations, and those rupture of contacts. And that's what characterizes their density. And I also had what are they affected by, are they marginal or not, and in which phenomena are they involved. So it could be a time point to take questions on that. Actually, it's we could last for longer. Right. So I had some other slides about open questions, but I think that was already very long. So yes, you can clap. Indeed, Julio, start.